All right, in this lesson, we're going to be talking about related rates. Related rates are situations where we have equations that have derivatives in them that relate to time, all right? And so we're going to see some examples here as we get into one, and some guidelines here, all right? We're going to find all the quantities that need to be determined. We're going to make a sketch, and that helps, okay? Write an equation that involves the variables whose rates of change are going to be determined. Use the chain rule to implicitly differentiate both sides with respect to t, all right? So time t. It's all about time. Rate needs time. All right, then after that, we're going to substitute and solve, all right? So we're going to start with a rectangle here. That's moving, that's stretching. And let's get a picture of it. So here we have this moving rectangle. So it's changing, and what's happening is it's changing at different rates, okay? So now this one's kind of bouncing around at random, but you can get an idea of what's going on, all right? So the length and the width, so if this is the length and this is the width, they're changing at different speeds, all right? And as the length and the width change, the area changes and also the perimeter changes, all right? So we want to find out how quickly the area and the perimeter are changing when we have these certain things true. So let's investigate this a bit here. So we know that the length of the rectangle is, let's say at some moment in time, is decreasing by 2 inches per second. Okay, that's the length. And the width is increasing by 3 inches per second. Okay. And we know that when the length, at one moment in time, we know that the length is 10 inches and the width is 6 inches. Okay, so a stationary picture can be very helpful. And we saw that kind of thing moving there. And so we've got a rectangle with length and width. We know that at some moment in time, the length is 10 inches and the width is 6 inches. Okay, and we also know that dl dt, the change in L with respect to time, is minus 2. So it is changing, it is shrinking by 2 inches per second there. We know dw, the change in W with respect to time, is positive 3. It's growing, okay? Now, what we need to do is we need to start with a primary equation, kind of like we did in the optimization sections. Okay, we need to start with a perimeter problem. So let's think about perimeter. Perimeter is 2 times the length plus 2 times the width. So we need a starting equation here. All right. Now, what we need to do is we need an equation that can fit these things, an equation that involves these things. But notice there's no derivatives over here. Well, let's get derivatives with respect to time. So what we're going to do is we're going to take the derivative here with respect to time, and we'll take the derivative of this with respect to time. So notice, as we look over here at this thing, which is, let's get it moving again here, okay, the length and the width are dependent on time. They're always changing, so they are functions of time. Kind of complicated functions that we may not totally understand, but they are functions of time. We don't have to have that function written to know they are functions of time. Okay, and so everything's changing with time is the idea. So we can write this. This is dp dt. Okay, and now we're going to take the derivative of each of these parts here. And so we got, this is 2 dl dt. This is 2 dw dt. Sometimes we'll end up with an L and a W in here, but here it's just, they're all differentials. So this right here, little vocabulary, all right, this expression right here is called a differential. This is a differential equation. So differential is just an expression or a fraction that is a derivative. All right, so that's the change in the perimeter. So now we just need to plug things in here. And we were given some change in the length over the change in time. So we just got to plug those in there. And notice there's no W or L. All right, so we're just plugging in the dW dt and dL dt, okay, which are just values. So those are values that we know. So dB dt equals 2 times dL dt, which is -2, plus 2 times dW dt, which is 3. A little arithmetic. What do we got? -4 plus 6. That's -2. So that means a positive 2, sorry. So that means it's shrinking there. That's 2, and this is perimeter. Perimeter is inches per second. That's the key there. So we start out with our perimeter equation, take the derivative, substitute what you know, and solve it up. Now, let's look at the area. What's happening to the area? Well, we're going to need to start with an area formula in terms of length and width. And we know area of a rectangle is length times width. So now we have the dL dt. We want to figure out how fast it's changing. So it's changing. That means dA dt. So we're trying to find dA for area with respect to time. Well, the equation that we have doesn't have dA dt in it, so we're going to need to take a derivative. So we have a new equation that has dA dt. So we're going to take the derivative of the left side, and we're going to take the derivative of the right side. Okay. Now we're going to have to use some product rule actually here. Okay, and remember, A is a function of time. L is a function of time, and W is a function of time. So dA dt is equal to, let's use our product rule, derivative of the first times the second plus the first times the derivative of the second. Okay, we don't exactly know. Well, actually we were told. Now we're going to go, we know that, so we use the product rule. We know the derivatives with respect to time there. So we're going to substitute these things that we know here. So there it kind of just jumped. But what happened there? We plugged in dL dt, we plugged in dW dt, we plugged in the length here, and the width at that moment in time. All right? And so when we plug in all those quantities into our function, we end up with 18 square inches per second. Remember that this is area, and area is square inches. That's how much the area is changing. All right. Well, let's look at a volume function here. Okay. So here we got a spherical balloon, and it's being inflated at a constant rate. We've got something blowing it up, and that constant rate is 5 inches per minute. Cubic inches, that is. All right, and we're going to investigate it at some moment in time. There's a moment in time where the radius is 4, and we want to figure out how fast the surface area is changing. Okay, so let's translate that into expressions. Okay, so we know that is being inflated at a rate of 5 cubic inches per minute. All right, cubic inches is volume, so that's a change in volume. dV dt, the change in volume, is 5 cubic inches per minute. We're trying to find the surface area, ds dt, We don't know what that is. Okay, that's what we're trying to find here. Okay, gotta be careful with 5's and s's. They look a lot alike. All right, so d, we could even say surface area, dt, that's fine. Okay, so we're trying to look for that. We also know that at some moment in time, the radius is 4. So again, we're going to start with the generic equation, take the derivative, and substitute what we know. All right? So our generic equation here for volume is volume equals, for a sphere, it's 4/3 pi r cubed. Hopefully that rings a bell a little bit from geometry. Now, we need to find, we need an equation that has the derivative in it, okay? So we need the derivative of volume. So let's take ddt of this side, and we'll take ddt of this side. So we get dv dt equals, now 4/3 pi, that's just a constant, so that's just going to pop out. Now we're going to take the derivative of r cubed. Okay, r is a function here, so this is implicit differentiation. So we need to take the derivative of the outside, which is 3r squared. But you got to also multiply by the derivative of the inside, which is dr dt. Now this one has a little twist here. What are we looking for? We're looking for a surface area. There's no surface area in that equation. Well, we need to use dr dt. Okay, we're going to use dr dt to figure out the surface area. Okay. So, what does this tell us? We know dv dt, that was 5. Okay, and we have 4/3 pi. Actually, let's go ahead and clean this up. This 3 times this 3 is 4. Or they cancel, I should say. So we have 4 pi times 5. What's the radius? Well, the radius is 4. All right. So the radius is 4. So, and then we got dr dt. So we simplified here. And then substitute for what we know. We know dv dt. We know r. We don't know dr dt. So let's see what this does for us. Okay. So we have 5 equals 4 times 4 times 4 is going to be 64 pi dr dt. So if we solve this, we get dr dt equals 5 over 64 pi. So now we know the dr dt, the change in r. So let's think about our surface area now, because we're going to need ds dt. So the surface area formula for a sphere is 4 pi r squared. So now we're going to take that, and we need to find ds, or derivative of surface area with respect to time, ds dt. So let's take the derivative with respect to time. That gives us dsa over dt. We've got a constant again, 4 pi, just hangs out. And we need r squared. We need to use a chain rule. Derivative of the outside is 2r. Derivative of the inside is dr dt. Doing that implicitly. All right, so we have 8 pi r. And what is r in this case, or at this moment in time? It's 4. And dr dt, what is that? That's 5 over 64 pi. So we're just substituting dr dt into there. Okay, 4 times 8 is 32, so this is 32 pi times 5 over 64 pi. Some canceling going on here. And that leaves us with pi goes away, 32 goes away, leaving 2. So the derivative of surface area, the change in surface area with respect to time is going to be 5 halves. And this is area, so this would be, what's our units here? Inches is inches. So this would be square inches per minute. And that's the change in the surface area. So that's the idea there. Once again, a little overview. Start with a function that relates the variables, a known function like this volume function here or this surface area function. And then we take the derivative and we'll get a differential equation that has derivatives in it and non-derivative variables. Okay? And then we substitute and solve. All right, that's the general process for finding or solving a related rates problem.